Good evening, everyone. It's Glenn from Park Transit. Second video in my coding series in regards to trying to use software to code an occupancy solution where a camera will count the cars in a car park. Okay, so I was going to do a solution based on a webcam all the way in Tennessee University, where there was a campus webcam on their car park, but that seems to have changed. So I've decided to use my local car park at the lighthouse at the Wollongong Headlands. And this, you see an image here, this is the car park in question. That's the second image. There is another image. Oops, I'm just going to try to find it. Okay, so this is an image. So this is the first image I took. This car was about to unpark, and I was holding the camera. It was a bit shaky. I didn't have a stand in this case, and the second image, the car's gone. So what I did is I ran a program to at least start to block out spaces. So here we go. I've got I had the code. The program is running now. Here's the first image. What I did is I created I squared off an area. And it's very difficult. You can do rectangles easily, but parallelograms or polygons are a bit more challenging. It requires a bit more skill, and you then have to define it. It takes quite a while. You have to get it exact. And funny thing is that, as you notice here, to defining where you're going to put that square is quite difficult. Preferably, the higher the camera will be, the easier you can look down upon the space and you can have a very clear cut. So if I had a red square around this Jeep, I wouldn't have any superfluous space. And this here, you can see that I only grab about a third of the car at most, and probably half of the space of interest, if that. So hence why a camera up high makes more sense, and you have less to figure out. The second image out of all of this then is what happens in that defined area when a car goes. Interesting things is that you have, based on the light, you have this water or oil, which creates some glare and it makes it difficult to block that out. Imagine if a car was there that was silver, the colors would be similar. Now, what I did in this case is that it's really hard to see the image, but if this is if you can just zoom, I can't zoom in on this image, but if you look closely at this image here, when my cursor is pointing in the middle, there is a parallelogram where you see that piece of the car that would have been within that red square. And I've made it into a grayscale, which seems to work better when you start to manipulate the filters. Now, when you put it, here's some filters here. I put it through, and this is basically the difference between this section with the car and the same section when the car left. And you can see here that on this right, I accidentally picked up the white line. That would have been this white line. That was a mistake. So I've picked up oil spill. I've picked up the curb. Yeah, so I'd have to really think about what forms of filters. There's various kinds of filters you can apply to figure out the difference. And then what I did is I looked at the difference and counted the difference. I basically counted the number of white pixels in this case. And in this case, I know it's very difficult, but it's 443 white pixels in this particular thing. So it seems simple, but it took a while to get all that definition, get the number of channels per image, and all this sort of technical paraphernalia. Now it's just a matter of applying computer logic to answer the best use of filters, so that I can figure out the difference between when the car is there and when it isn't, and to start to get more clear definitions so that I know a car is or isn't there based on the variation in the image. So that's it for now. So thanks very much.